This dataset contains a list of video game sales greater than 100,000 copies gathered from VGCharts.com. The data contains sales between 1980 and 2016 on over 11,000 game sales detailing their name, year of release, genre, platform, as well as sales data per million on North American sales, European sales, Japanese sales, global sales, and sales from other smaller regions. We wanted to find out how video game sales were affected by region, and which region had the greatest effect on global sales. Our data shows that North America accounts for over half of all global sales. Here we have several visual examples showing a linear relationship between regional sales and overall global sales. As we can see, North America and Europe are the closest to the trend line out of all different regions. If we look at our heat map, we can see that the two values that have the highest collinearity with global sales in the millions are North America and European markets. The two values from North America and European markets are highly correlated, and North America was much more collinear to global sales. For this reason, we decided to eliminate multi-collinearity and run a linear regression analysis, dropping European sales from our analysis in the process. After running our linear regression model, using our data from North American sales, we got a coefficient of 1.34, meaning for every million sold in North America, the rest of the world sold 1.8 million. This shows strong evidence that North America makes up a big chunk of global sales. We wanted to make sure that our results would stay relatively unaffected by any noise in the data. Our homoscedasticity shows that the data points stay pretty random on each side of the line in our residuals versus fitted values graph. Our group wanted to make sure that our data remained random and independent. In order to do this, we did an analysis of the normality of residuals and the mean of residuals. We wanted our value to be pretty close to confirm the value's random or independent nature from our normality of residuals, which we can see our value was pretty close to 0. We also analyzed theoretical quantile versus the sample quantiles, and the data points stayed pretty close to the line on this graph, which is just the way we want our data to look. We also wanted to make sure there wasn't any autocorrelation or any values that are independent from each other, that aren't independent from each other. The Durbin-Watson model shows that if the value is anywhere from 1.5 to 2.5, that means that there is a low chance for autocorrelation. And as you can see, our value is 1.927, so there is low autocorrelation. In order to analyze the strength of our model, we analyzed 4 factors: the mean absolute error, the mean squared error, the root mean squared error, or how well our prediction works in absolute terms, and the R2 squared value, or how well our prediction works in percentage value. With our mean absolute error value and the mean squared error, the lower the values, the better, and these values are very low, as you can see. The RMSE is 0.562, which gives us a predictive value with 85% accuracy.